Okay, now we're going to take all the stuff that we did for Captopril and we're going to do it one more time, but very quickly. And we're not going to make any reference to Captopril. We're just going to look at general principles. We're going to go over our 6 steps and we're going to put them on a slightly more solid footing. And what are we going to have at the end is our first hypothesis test, the so-called one-sample t-test, one of the workhorses of hypothesis testing. First thing that we're going to do is we're going to define our null hypothesis and our alternative hypothesis. As you already know, the alternative hypothesis corresponds to what we want to show, our research question. And for now, we're going to assume that that's an association between 2 variables, or that that's a statement about a mean. And it's very important to keep in mind that we cannot prove the alternative hypothesis. So we cannot go out and test everybody and then say something about whether or not the thing holds in reality. But what we're going to do is we're going to disprove the so-called null hypothesis, the opposite statement. Remember, null hypothesis is a skeptical perspective, nothing changes. And disproving the null hypothesis is not the same as proving the alternative hypothesis, but points in the way of that. Now, we're going to compute our test statistic to do that, to gather evidence against the null hypothesis, and the test statistic is always going to tell you how different the results of the sample are compared to those under the null hypothesis. And in the case that we are considering now, we're going to look at a test statistic given by sample mean minus 0, and that 0, one more time, comes from the 0 here on the right-hand side of the null hypothesis, over the standard error. The idea here is that the test statistic is large, means evidence against the null hypothesis, so reject null, and test statistic small means do not reject the null hypothesis. Okay, now we're going to have to be a bit more specific. When exactly are we going to reject the null hypothesis? So we are going to, roughly speaking, look for enough evidence that the null hypothesis is false, and that's going to correspond to the test statistic surpassing some chosen threshold value. So we'll choose a fixed value C, and then if T in absolute value is bigger than C, we're going to reject. But of course, I haven't told you what C is, so that's the next thing that we'll have to do. If the test statistic is not above that threshold, then we're not going to reject the null hypothesis. Means that we don't have enough evidence to decide the null hypothesis is false. Now, very important point to keep in mind. If we don't reject the null hypothesis, it doesn't mean that the null hypothesis is true. And conversely, even if the null hypothesis is false, the data may just be too weak to show it. You can make some analogies with legislative justice. If we don't find enough evidence to convict someone, it doesn't mean that that person really is innocent. It just means that we don't have enough evidence to convict them. If a person is guilty, if the person did a crime, which is the equivalent of the null hypothesis being false, it might just be that we have not enough evidence to show that they are in fact guilty. So to determine the threshold, we're first going to look at the p-value. That's going to help us to fix a good threshold. The definition for the p-value is exactly the same as what I gave you in the Captopril example. It is a probability to find purely by chance, i.e. if the null hypothesis holds, a result for a test statistic that is at least as extreme as the observed result. So the probability that the test statistic in absolute value is at least as large as what we found in our sample, given that the null hypothesis holds. And this is true for a two-sided test. For a one-sided test, it will be slightly different, but we'll get to that later. So the smaller the p-value, the more the results contradict the null hypothesis. And what we will do is, when the p-value is low enough, we will reject the null hypothesis. Now, be very careful with that definition of the p-value. The p-value is not the probability that the null hypothesis is false. This is actually a very common mistake to make. And a few years ago, there was a sort of a sad/funny story where a number of psychology journals sort of said like, hey, nobody understands what p-values are, so in our statistical reporting, let's not use p-values at all anymore. This was a bit an outcome of the fact that 10, 15 years ago, a lot of people started realizing that scientific work or statistical analysis was not as robust as it should be. And then they looked at why that is, and one of the results was basically like, yeah, people are misusing p-values to show something that is not there. And so this one journal did a very bold move, and they said, okay, from now on, if you write a paper, you're no longer going to use a p-value because we just think it's confusing. You're going to do something else. And then Nature, the famous Nature journal, wrote a small article about this decision. And in their article, they actually said, and I will read it, it's a false statement, the closer to zero the p-value gets, the greater the chance that the null hypothesis. Now with p-value, you have to be very careful about how you interpret it. This is another area where statistics is actually a little bit counterintuitive, and people make a lot of mistakes against this. The other area, of course, where it's not so easy and it's a bit confusing is the definition of what is a confidence interval. So these are two things that go hand in hand. They have very well-defined definition, but how you interpret them, you have to be very careful. In fact, about 10 years ago, there was a funny or sad, depending on your perspective, story. So there was general tendency in the scientific literature to re-examine the foundations of statistics because people realize like, hey, everybody gets it wrong. And because they do their statistical analysis wrong, then the conclusions also are wrong in some cases. And one psychology journal went very far in that, and what they did is they banned p-values from their articles. So they basically said, everybody gets p-values wrong, so let's not use p-values anymore anyway. And then Nature, the famous Nature journal, wrote a small article about that decision. And in their story, they wrote, the closer to zero the p-value gets, the greater the chance that the null hypothesis is false. But that is a statement that is wrong. That does not follow from the definition of p-value at all. It is in fact false. So then Nature had to issue a correction to say, hey, we actually also got it wrong. And that gives even more evidence to say like, yeah, p-values are very counterintuitive and you have to be very careful when you think about them. Okay, so now we have our p-value. How do we get to our yes or no answer? We're going to need a decision rule. We're going to say we reject H naught, the null hypothesis, at a given significance level if the p-value is smaller than a certain threshold. What are we going to do? Well, we'll quantify our significance level as alpha times 100%. So for example, we'll say at the 95%, at the 5% significance level, 5% significance level, if our p-value is less than 0.05. But we can also have other thresholds. We can say we reject H naught at the 1% significance level if alpha is less than 0.01, and so on. That significance level, that threshold, you are also going to fix before analyzing your data. it's very easy to have a p-value that is very close to being significant. So typically we use alpha equal to 5%. So it's very easy to end up with a p-value that's 0.51, for example. And if your significance level is 5, then of course that is bigger than 0.05. So here you would not reject H naught. Not reject H naught. But not rejecting the null hypothesis means our evidence was not strong enough to reject the null hypothesis. Basically means you did the experiment for nothing. You can't decide anything. And then it's very tempting to do the following thing. I will write it down. So do not do the following thing. Don't say, okay, I'm gonna ignore the fact that P is 5%. You know what? I'm gonna set secretly my alpha to 10%. If you do that, then now you would say like, hey, my p-value is less than that alpha, that 10%. So all of a sudden, now I'm allowed to reject my null hypothesis. And reject the null hypothesis means I found something and I can write a paper. So don't do that. That is very, very heavy scientific fraud. Fix your significance level before doing the experiment, and then don't change it and just accept the results that the data give you. Okay, so we can summarize what we've done so far and go a little bit further actually. So we will reject the null hypothesis if P is less than our significance level, alpha. But we also know that for a two-sided test, my P is the probability that the test statistic in absolute value is bigger than what I have in my sample. And here I have to be precise, assuming that the null hypothesis is true. And we've already seen that that's probability in the positive direction, so probability that t is bigger than absolute value of t given h naught, plus probability that t is less than negative absolute value given h naught. And now we can go to the drawing here. The probability that t is bigger than absolute value of t, you're going to find that here. And the probability that t is less than minus absolute value of t, you're going to find that here. So what we're basically asking for is we want those tail ends to be not too large. We want the part on the right to be no bigger than alpha over 2. And we want the part on the left to be no bigger than alpha over 2 as well. Because together they should be at most alpha. Now you can take that probability and you can look at for the quantile that corresponds to those probabilities. And that will give you these quantiles right here. And if you're wondering how we find these, calculation is exactly the same as what we did in the previous slide deck on confidence intervals, except now we're working with a student t-distribution, and there we were working with a normal distribution. But the principles are exactly the same. You can do the same thing and just replace normal by t-distribution. And what you're going to find is that these quantiles give you precisely the critical value that you need. More precisely, we have the second expression right here. If your test statistic exceeds quantile t of n-1 degrees of freedom 1 minus alpha over 2, then your probability, your p-value, is going to exceed your or is going to be lower than your significance level alpha. So you have two options. Either you compute the p-value and you look, is p less than alpha? Or you compute your test statistic, you take the absolute value, and then you say, is that absolute value bigger than that critical value, that quantile of the t distribution? If either one of those is true, then you reject the null hypothesis, and otherwise you don't reject the null hypothesis. And once again, these two conditions, they're equivalent. You have to compute only one, and then the other follows automatically. So that gives us our first hypothesis test, the one sample t-test. What are you going to use it for? To verify if the mean of continuous measurements deviates from a certain value mu0. Steps, very quickly, you're going to formulate your null and your alternative hypothesis. So here I've written it in terms of a arbitrary mu0. Typically mu0 will be 0, but not always. You're going to check that your conditions hold. You're going to compute your test statistic. You're going to, very good idea, it's optional, but very good idea nonetheless. You're going to draw a figure to show where your test statistic is. You're going to compute your p-value. You're going to compare with your significance level, and then you're going to make a decision. Reject the null hypothesis or not. In R, running a one sample t-test is very easy. You just have to use one line of code. There's a t.test command in R, and you give it a vector of observation. So here this delta is the vector that consists of captopril after minus captopril before, and that is the vector of your differences. R will then spit out a little textual summary of the test that it does for you. So it's going to tell you, yeah, I'm running a t-test. It's going to compute the test statistic for you. We've already done it in my hand. It's good to see that it's the same. It's going to tell you the number of degrees of freedom, 14, because we had 15 patients in our study. And it's going to give you the p-value. It's also going to list for you the alternative hypothesis, and then it's up to you to inspect the p-value, to compare with your significance level, and to decide what is true. What else do you get? You get a 95% confidence interval. We already computed that in one of the previous lectures, I think. And you get, for good measure, the mean of X as well. So now we can understand everything that's in that output. Okay, and then just to finish up, I want to set a problem for you, but I will make a Quarto document available that you can work through. So here is another research problem. So we have bighorn sheep in the Rocky Mountain, especially mama sheep that give birth to little sheep. And what we want to know is whether lactation, weaning, demands such amounts of energy from the sheep that they would have to graze more during the lactation period. The experimental setup is as follows. We have 16 sheep. We make two measurements for each sheep, once during the lactation period and once outside. We're going to run a two-sided test to look for a difference. We're going to set the significance level to 5%. Our null hypothesis is that the mean difference in grazing time during lactation and outside lactation is 0, and the alternative is the opposite, that is not 0.